Consider major aeronautical revolutions. A few may come to mind. For example, the first flight at Kitty Hawk, or breaking the sound barrier at Edwards Air Force Base, or perhaps the massive buildup that led to humans leaving Earth to explore other planetary bodies. While these achievements are extraordinary, one key aeronautical revolution that is often overlooked is the standardization of commercial flights into the National Airspace, or NAS. It may seem simple enough and often not widely understood by the flying public, but our national airspace infrastructure is huge. It comprises the navigation facilities and airports of the United States, and all the services, rules, regulations, policies, procedures, personnel, and equipment. Every day, more than 44,000 flights safely take off and land here in the U.S., totaling more than 16 million flights per year. This process is seamless to most of us due to the dedication of millions of professionals who work to provide safe flights in and out of the national airspace. When a complex system this big works so seamlessly, great care must be taken when new advancements are added into it. Over the years, there have been incremental changes to the system, but one major advancement that is happening now is the integration of unmanned aircraft systems into the national airspace. That may sound innocuous enough, but updating our current national airspace to include millions of unmanned aircraft is a Herculean task that has required years of research, study, and countless hours of design and analysis to move this task forward. This integration needs to be seamless, keeping the flying public safe while also allowing new vehicles to perform their assigned tasks. On this episode of NASA X, we'll follow researchers from NASA and industry to better understand how unmanned aircraft systems will be integrated into the National Airspace System. We will also shadow a unique flight test that joins pilots, engineers, and researchers together to help establish standards for piloted and unmanned aircraft flying in the NAS. Join us as we uncover this complex endeavor and find out what the future of flight looks like for UAS consumers and the flying public. On this cold morning in California's high desert, a group of researchers from NASA and from industry are preparing for another fact-finding flight using the Navarro Applied Sciences TIGERSHARK XP. NASA Armstrong, located at Edwards Air Force Base, has seen many important test flights over the years. But this flight, and the others performed by this group, are being used as building blocks for research that is enabling a paradigm shift in flight as we know it. This round of testing, known as Flight Test Series 6, or FT6, is assisting the Federal Aviation Administration as they develop regulations to allow the integration of unmanned aircraft systems into the National Airspace System.
The work that we're doing will contribute for others to come after us and know how to safely integrate this type of airplane into the national airspace. So a lot has gone on to integrate manned airplane into different parts of the airspace. So the same level of effort, or perhaps more, needs to go into integrating unmanned airplanes. There's different options on how you do that. There could be a pilot on the ground, which is what we're doing right now, or the airplane could be doing things on its own. Before you let the airplane go do things on its own, we would need to be able to anticipate all the sorts of things it can see and know how it would safely respond to those things. So the work that we're doing will eventually help get us there, whether we have a pilot on the ground either monitoring or actively controlling the unmanned airplane, or if the unmanned airplane can do something on its own that whatever it does will be safe to the traffic around it and to the people under it.
Unmanned aircraft have come a long way over the past several decades. Once, they were relegated to toy status and for military use. But now, there are many different applications for UAS use being studied, like package delivery, helping with crop production, disaster relief, and even transporting people. With this increase in UAS numbers, the FAA realized that integrating these remote-controlled and autonomous aircraft needs to be prioritized.
Well, NASA has a dual purpose in this. One is to do the basic research that is required to understand what is needed to integrate the UAS into the NAS and to help us do the early research to determine what other regulations are needed, the policies, the guidelines, those types of things, and what's the information we need in order to issue waivers and certifications and those things. At the same time, they also have a responsibility or a goal to assist industry in letting them know what's necessary for them to produce and operate UASs in the national airspace.
So with the help of NASA and the aviation industry, new, small, lightweight, and low-powered sensors to help conventional aircraft and UAVs detect and avoid one another are being evaluated.
The FAA has a mandate, obviously, to make sure that we have airspace that's safe, but also that they enable the utilization of aircraft and technologies that really benefit the American public. And it's clear there's a lot of industry pull for the FAA to come up with rulemaking and some standards that would enable some of these newer platforms, these newer use cases. And so if there turns out there's a use case for delivering a pizza, we want to make sure that the FAA has come up with a way to do that safely. If there's a use case to get your birthday present delivered to your front door by an unmanned vehicle, we want to make sure that the FAA has enough information to really be able to allow a company to do that safely. And so these demonstrations were really meant to look at those enabling technologies, figure out maybe what the pitfalls and what some of the limitations are, but ultimately to inform the FAA so that they can do the rulemaking that's needed that will really open up some of these markets.
So detect and avoid, in particular, manned pilots have a responsibility to see and avoid other aircraft when they're flying in the airspace. And when you take the pilot and put them remotely in a ground control station, we still have that responsibility. And so pilots we need to use other sensors to detect other aircraft and then develop algorithms to help them determine how to avoid those other aircraft.
As Jay mentioned, one of the primary safety concerns with integrating these new systems is the inability of remote operators to see and avoid other aircraft. On all flights with pilots on board, the FAA requires the crew to be aware of all other surrounding aircraft, either visually or using onboard instrumentation. In addition to instruments, the pilot physically looks out the window to help safely avoid other aircraft. Because unmanned aircraft literally don't have a pilot on board, NASA and its partners have been working on concepts and designs that will allow safe operation within the national airspace. That is where FT6 comes in. Since 2011, NASA has incrementally been evaluating how to help remote pilots safely detect and avoid other aircraft by systematically testing and developing new concepts and standards.
From the very beginning, of course, the first thing was to essentially integrate the payload, which is the detect and avoid system, into the aircraft. Once we did that, then we go through a series of system checkout flights just to make sure everything's working. Whatever we learn from that in terms of from a safety standpoint and also from a functionality standpoint, then we make corrections and basically improve on that. Once we verify that the system is working, then the next step is to essentially introduce intruder aircraft to verify that the displays and the alert and guidance systems work and get feedback from the pilots as well. And those rehearsals basically are to set up for what we call the full mission, which where we are right now in that phase.
In this final phase of FT6, NASA and its partners will be working to support development of Minimum Operational Performance Standards, or MOPS, for detect and avoid for medium-sized UASs utilizing small, lightweight, and low-power sensors.
From our side, we're pushing the boundaries for this small aircraft. We're trying to fly a radar that's small, tiny, and trying to pick up aircraft, and they're trying to define what that is. Again, it's a brand new radar, state-of-the-art systems. They don't really exist out there. Low swap systems don't really exist for aircraft. When you're dealing with smaller aircraft, a lot of it's hobby grade type of systems, avionics. A lot of it's not conducive to flying real aircraft. But now that we're actually trying to fly in the national airspace, we need to put real avionics on there, things that are tested to FAA certification. And that's pushing the boundary. I think that's what we're doing here with this low swap system.
So how is the NASA team pushing the boundaries? By using a number of unique control centers, piloted aircraft, and a UAS with a large number of flight hours to supply the needed information for integration. FT6 is a multi-dimensional test with many different groups of researchers and pilots working together to make sure the test goes according to plan. During each flight, there are several different researchers in different control rooms monitoring the flight, and there are also at least 3 layers of pilots in the air and on the ground. To better understand this complex dance, let's first look at the UAS that is being used. For this round of testing, NASA decided to use the Navarro Applied Sciences TIGERSHARK XP UAS. This is a medium-sized aircraft with a wingspan of nearly 22 feet and can stay aloft for 12 hours. It's controlled remotely using a ground-based cockpit and has been equipped with a smoke-generating system to assist the intruder pilot with visibility and an early developmental low-swap nose-mounted radar built by Honeywell that will use a fixed-phase array to steer the radar beam electronically.
The TIGERSHARK is a Group 3 unmanned aerial vehicle, 500-pound weight class, and it has been used as basically an R&D platform to enable NASA and NASA's partners to test various pieces of software and hardware to help develop standard operating procedures for integrating UAS into the national airspace relative to detect and avoid technology component.
Because this UAS platform has such a long and stable track record, the FT6 team felt that its reliability would allow them to focus their expertise on testing rather than worrying about building their own UAS. One of the most intriguing aspects of this test is the different roles and assignments performed by the team flying the UAS. The Navarro team pilots the aircraft during the initial takeoff and landing phase, but after the craft is airborne, control of the UAS is handed off to NASA pilots. The subject pilots that take over the flight are not aware of when intrusions into the airspace would occur, making it realistic to what pilots in the NAS would experience.
Open Center NASA 01, deviating for traffic 170. Open Center NASA 01, clear of conflict heading 030.
They must be able to react quickly without anticipating a solution to a scenario before the encounter has even occurred.
This is a subject pilot station, so what they're observing is the on-ship aircraft, and then they'll see intruder aircraft. The aircraft are generated by either virtually from AIMS, and that's just to add background traffic to kind of create a real airspace system. And then you have real traffic that's picked up by the aircraft systems, and that's injected through the payload and it comes into the system too. So they're getting a mix of both real traffic and virtual traffic. And all they're doing is essentially flying this mission. They'll get intruders coming in and causing traffic alerts. If it's a yellow alert, they'll either talk to ATC and move, or if it's a red alert, they'll move immediately, then talk to ATC and coordinate on their way back. This all done in Oakland airspace in a virtual environment from their side, even though they're flying the real aircraft with real intruders.
We were actually able to gather a lot of the metrics that you would normally gather in a lab, but in this case, a real atmospheric flight. And that's what we call live, virtual, and constructive. We had the live component, which is the live UAS and the live intruder. The constructive, which were traffic, simulated aircraft that were moving in the airspace. And then virtual, which were actually people who were flying simulated aircraft and talking over the radio. And all those things combined to create a really immersive test environment.
So this is the Mobile Operations Facility 5, MOP 5. So this is the NASA Ground Control Station. This is where we execute all the flight testing, all the missions conducted from this. So this system's interface to the Navarro ground station. It's interfaced to the LVC environment, and it's interfaced to the comm system here at Armstrong. So again, interfaces to all the systems and allows us to communicate with everything. So from here, once the aircraft's airborne, our pilots take control of the aircraft, move it into the airspace, and then after that, control is transferred to the subject pilot that's on this side of the station. And this is where we conduct the mission, the full mission for the flight test. So the subject pilot is not familiar with the system, and that's done on purpose. It's a human factors research. We need trained pilots to actually monitor the airspace and make sure that we're still flying in real airspace. And in an actual Edwards Air Force Base, there's actually other missions going on in the background. So we need our pilot test to manage that part of the test and call it off if they need to, or take control of the aircraft if there's an actual emergency up in the air, or if there's another mission that's intruding.
These piloted aircraft are not only employed as chase planes, but are used to intrude in the airspace around the UAS to test the detect and avoid system. During these flights, intruder aircraft intentionally fly very close passing encounters to the UAS, which trigger the DAA alerting and guidance. These encounters test the detect and avoid procedures, helping researchers develop performance standards to address such scenarios. A typical test day starts off in the early morning hours. The team starts with a T0 briefing. During this time, all team members go over all the test parameters for the day. Once that briefing is complete, everyone goes to their respective locations, such as control rooms or to the aircraft. When everyone is ready, there is a comm check over a specific frequency. Meanwhile, the TIGERSHARK is towed out to the lake bed for launch, while the intruder aircraft are preparing for takeoff. Once on the lake bed, a series of tests are performed on the aircraft to ensure it is safe and ready to fly. When all these tests are complete, the ready call is given, and the aircraft is set for takeoff.
And we got good RPMs, good systems, brakes off.
52, 53, 55.
On this cold, clear morning, the aircraft takes flight without a problem to begin the day's test. Once airborne, the NAVMAR team hands over control to the test pilots to fly the mission for the day.
PUT, this is AVP on mission, ready for handover.
PUT, ready for handover.
Your aircraft, just report.
PUT has the aircraft, Wilco.
In the various control rooms, teams of researchers are monitoring the system, while intruder aircraft begin the incursions into the UAS airspace.
Tiger 50310 heading as approved.
Right turn 320, 335.
On this day, each pilot sees the incursions and properly guides the aircraft away from the intruders.
Correction, right turn 350.
This test continued for several hours, with numerous intrusions occurring. As the test winds down, flight control is given back to the NAVMAR team, who then brings the TIGERSHARK back for a perfect landing.
I've seen a trend so far working in the industry, and it's only continues to climb. When I first started, quadcopters or large UAS weren't really a thing, and now we've flown a large UAS in the National Airspace for the first time, and now we're working towards integrating a smaller class UAS into the National Airspace as well. Eventually, everybody wants to jump in a taxi and have it airlift you from building to building. This technology, this detect and avoid technology, will really help that and conduct it safely.
Over the course of this comprehensive testing, NASA and the FAA have amassed an enormous amount of data, allowing safe, efficient integration of these systems into the national airspace. This type of result is not unusual for NASA and its partners. Over the past 60 years, this organization has continued to push the boundaries in science, engineering, and technology. While the presence of drones and unmanned aircraft begins to populate the skies, NASA will continue to test, evaluate, and pursue a safe and efficient airspace that will coexist with commercial and private aircraft. What many thought was science fiction will soon become science fact as these aircraft become a part of our everyday lives.